Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and I'm looking forward to making this video today. This is something that I've wanted to do for a long time. Today we're going to talk about the transit of Venus and how it was used to determine the distance from the Earth to the Sun, or 1 astronomical unit. Now, I'm going to have another series that talks about the expeditions for the Great Transit of Venus in 1769. And a lot of very famous names: Captain Cook, Benjamin Franklin, Mason and Dixon. These were all involved in that transit of Venus. And it took place during wartime. There was piracy and just a really exciting story. But that's a tale for another time. Today we're going to talk about the actual nuts and bolts of how it is done mathematically. So let's cue up the music and get going. Well, first things first, let's go over the basics. Now, the transit of Venus used something called parallax to measure the distance from the Earth to the Sun. Now, parallax is actually a very simple process. Say we have two lines. We've got one that goes here, and we have one that comes down here. Now, both of those lines see an object. So obviously, the object is located here where those lines crossed. But if you were to look at that object on the disk of the Sun, perhaps, you might see this one down here, and you might see that one over there. This distance between the two is called the parallax angle. Now, it was the parallax angle that was used by Cook and the others to determine the distance from the Earth to the Sun. First, by determining the distance from the Earth to Venus during a transit of Venus. Now, let me show you what a transit of Venus is. Now, every 120 years, Venus passes between the Earth and the Sun. It does it twice, and those two episodes are 8 years apart. Now, there were transits of Venus in 1761, and there was another one in 1769. And more recently, we had a transit of Venus in 2004 and another one in 2012. The next transit of Venus will not occur during our lifetimes. Now, what you see on a transit of Venus is, if you look at the Sun, you will see a small dot that represents the planet Venus. And that dot will trace a path across the Sun like so. And here's an example of that. So here's a transit of Venus. I don't know if this was 2004 or 2012. It was probably one of the two. Now, the interesting thing is, if you go to a different location on Earth, preferably one that's several thousand kilometers away, you'll also see Venus track across the face of the Sun, but it'll track in a different area, say here. And the difference between these two is called the parallax angle, and it is related to how far apart the two observers are. Now, you can use this to determine the distance from the Earth to Venus, and the formula for that is very simple. Distance equals the base, which is the distance here, over the angle in radians. Okay? Now, back in Captain Cook's day, there wasn't worldwide communication. We couldn't do simultaneous observations. So what they did was they measured the location of that line. What they looked for was, as soon as the planet Venus was fully within the Sun, they started a clock. And they kept that clock running for the six and a half hours that it took for Venus to just touch the other side of the Sun. Venus goes across the face of the Sun at a fixed rate. So this shorter line will take less time to make that crossing than this longer transit here. And the way you determine how long those lines are is you measure the time it takes Venus to go from fully in the sun to just as it's starting to leave. The other two times that you could look at it is when it's just outside the sun, both coming and going, but those are very difficult measurements to make. It's much easier to just pick the very instant that you start seeing light between Venus and the edge of the sun. That gives you a very accurate timing to make these lines. Now, that's actually a little bit more complex than the method that we're going to use today. Today we have the ability to do instantaneous measurements all over the world. We can coordinate them on time. So for example, say we had an observer in Princeton, New Jersey, and we had a second observer at the top of Haleakala, which is a mountain on Maui. The distance on the surface between those 2 points is 78.31 kilometers. Now, if both of those observers took a photograph of the transit of Venus at exactly the same time, Venus would appear in 2 different locations on the sun because of the distance between those 2 observation points. Now, by measuring the distance between those 2 images, you could get an idea of what they call the parallax angle. That parallax angle is this angle right here. Now, knowing that angle and knowing this base right here allows us to calculate the distance from the Earth to Venus. So let's go ahead and have a look at this observation, and I'll show you what we're talking about. Now, here are the 2 photographs that were taken. The top one here was taken in Princeton, New Jersey at Princeton University, and the bottom one was taken in Hawaii. Notice that Venus is visible in both of the photographs. The other thing that we have is some sunspots. You see these sunspots? Now what we can do is we can actually line those sunspots up after we adjust for the different focal lengths to make sure that these 2 suns are exactly the same size. Then we rotate one so that these sunspots all line up. The result is that we get 2 silhouettes of Venus on the sun. And by measuring the distance between the centers of these silhouettes, we can get a parallax angle. Let me show you how they did that. So here are our 2 silhouettes of Venus. What we do is we measure how far down we have to go and count the number of pixels, and then how far over to the right we have to go. By squaring this side and this side, we get the square of that side. That's the Pythagorean theorem. So what they did was they went ahead and measured that, and what they came up with was 27.39 pixels. Well, now we have a little bit of a problem. How many arc seconds are in a pixel? Well, that's easy enough to find out. So on the day of this observation, and the diameter of the sun was 31.57 arc minutes. Now an arc minute is 1/60th of a degree. Now what we need to do on this particular exercise is we need our angles in radians. So we're going to convert everything to radians. So the way we convert that to radians is rather simple. So we have 37.51 arc minutes. All right. In 1 degree, there are 60 arc minutes. So now we have our answer in degrees. Finally, we convert to radians. Now what a radian is if you take a circle, and that circle will have a radius to it. If you look at the circumference of the circle, there'll be a certain part of that circumference that is equal in length to the radius. So basically that's 1 radius length, that's 1 radius length. So how many radians are in a circle? We know that there are 360 degrees, but how many radians? Well, what's the formula for a circle? It's 2 pi times the radius. So there are 2 pi radians In a full circle, that's 360 degrees. In half a circle, there's 1 pi radian, and that's 180 degrees. Each radian is about 57.3 degrees. So, right now we have our answer in degrees. To convert to radians, we multiply by pi over 180, and that's 180 degrees. So now, our arc minutes cancel out and become degrees. Then our degrees cancel out and become radians. Now the last thing that we need to know, this tells us how many radians are in 37.51 arc minutes. The next thing we have to do is we have to figure out how many radians per pixel. Now the sun images in those photographs were 2460 pixels in diameter. And we know that that number of pixels equals this number of radians. So using that, we can actually calculate the size of the sun in radians, and we can calculate the parallax of Venus in radians. So let's go ahead and put those up. So here's the numbers that we got. For the sun, it's 0.009183 radians, and that's the distance from here to here, the diameter of the sun. Now, the parallax of Venus between the two silhouettes of Venus is 1.0224 times 10 to the negative 4 radians. All right? But there's a little problem with that, and that is that just as there's a parallax angle with Venus, there's also a parallax angle with the sun, and we need to correct for the solar parallax, they call. And when we do that, and the mathematics are in that paper that's attached to the description. So when we do that, we have this as the measured parallax of Venus, but the true parallax, the corrected parallax of Venus, is a little bit larger, and that is 1.429 times 10 to the negative 4 radians. So it's a little bit bigger. Well, now we've got one more calculation that we have to do. So this is an important calculation right here. 1.429 times 10 to the negative 4 radians is the parallax of Venus. Now what we have to do is we have to figure out the base of that triangle. Well, how do we do that? The distance between the two observer locations, by my measurement, is 7,831 kilometers. Now, while he did it a little bit differently in the paper by counting pixels, for example, I'm actually measuring it based on the great circle distance between the two locations, and I'm coming up with this angle right here, angle alpha. Now, what is the base of the triangle? It's this altitude line right here. It's not the distance along the surface of the Earth, which is curved and longer. It's this partial chord length between the two locations based on this angle. And the way that you would calculate that is that's the opposite side. So you would take the sine of that angle, and it comes out to 6,007 kilometers. So it's considerably less. Now we're actually ready to calculate the distance to Venus. Okay, so let's go ahead and put some numbers in. Here's our formula. Distance is the base length over the parallax angle. Now the base length is 6,007 kilometers. And the parallax angle is 1.429 times 10 to the negative 4 radians, and we have that here. Now by doing that simple division, we come up with the distance between Earth and Venus, and that would be 42.04 times 10 to the 6 kilometers. So that's 42.04 million kilometers. Now, we're not quite done yet. So that is the distance between the Earth and Venus. That is this distance right here. Now those are the critical values that we need to know. We need to know the distance to Venus. Well, now we need to take a visit to Mr. Kepler. Now the definition of one astronomical unit is the distance, the mean distance from the Earth to the Sun. Now the way they figured that out is it's related to the time it takes the Earth to make one complete orbit around the Sun. That's 365 and a quarter days. Now, Venus orbits the sun faster. I think it's something like 274 days. But the bottom line is this. When you plug that in, you find that the distance from the Earth to the sun is 1 astronomical unit. The distance from Venus to the sun is approximately 0.72 astronomical units. Now, just to make sure that this is nice and accurate, we said that Venus is about 0.28 astronomical units from Earth when they're lined up like that. So what we would do is we would divide 42.04 times 10 to the 6th by the distance from the Earth to Venus. Now, I'll use the actual number here, which is 0.2887 astronomical units. And when we do that math, we come up with 1 astronomical unit equals 145.6 times 10 to the 6th. So 145.6 million kilometers is 1 astronomical unit. The correct number is 149.6. You know, that is pretty close for 2 guys taking a picture of the transit of Venus, one in Hawaii, one in Princeton. You know, they probably did this, you know, between classes. So coming within 3% of the correct value, simply by taking 2 pictures at the same time and doing a little bit of math, pretty easy. Now, one of the things that I kind of do is I debunk the flat Earth occasionally. And a lot of people in the flat Earth say that we have no idea what the radius of the Earth is. And that may be. All right. So let's go ahead and just humor them. Now, if we can't calculate this distance because the Earth is not a sphere, it's instead flat, well, what's the distance between the 2 points? It's 7831 kilometers, because that would be the flat Earth distance between those 2 points. Now, they seem to think that the sun is some 3,000 miles above the Earth and is about 30 miles in diameter. Those numbers will actually give you a larger value for 1 astronomical unit than what we got here, because you're dealing with a larger baseline. And recall, the base is on the top of the equation. Well, that was kind of fun. I hope it didn't get too confusing. I did include a copy of that paper in the description. I think that if you look at it, it's very nice, and he's got some good illustrations with it as well. The other thing that I want to talk about is that I'm going to start a series on the Great Transit of Venus in 1769. Now, there was a transit in 1769 and another one in 1761. 1761 was kind of a half-hearted trial. It was in the middle of the 7 Years' War. You had scientists from both sides trying to get these observations and work with each other while their countries were busy blowing each other out of the water. It's kind of an interesting story because the British Royal Society was in communication with the French Royal Society. What they ended up doing was they ended up going to the British Admiralty and getting a pass for the French scientists to go through English lines. So if an English ship pulled over the French ship, you know, they had these orders that said, hey, we're doing God's work here, let us go. And they would let them go. You know, it's a great story because, you know, the names that were involved, Ben Franklin, Captain Cook, Mason and Dixon, were all involved in these transit observations. And, you know, there's tales of piracy, and they're out in the middle of Siberia and South Africa and in the South Seas and Fiji. And, you know, there were 150 teams that reported back in 1769. It was the first true cooperative international scientific endeavor. And it really was an amazing story. And I'm using the book Chasing Venus as the background information for this. And I would highly recommend that you get a copy of that book because it's a great story. So this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. I hope that this wasn't too confusing and that you got something out of it. At least when people talk about the transit of Venus and they say, well, and they had to estimate the size of Venus, you'll realize that they have no idea what they're talking about because there's nothing about the size of Venus in this. It just has to do with a position. They're talking about somebody else, which was a transit 120 years before Captain Cook was out. So in any event, take care, guys. Remember to hit that like and subscribe, and I'll see you again soon.
the science guy.